On average, the electron cloud of an O2 molecule is distributed symmetrically across the molecule. The molecule is not polar. A water molecule, which is polar, repels the electron cloud, causing it to be asymmetrically distributed and thereby induces a dipole in the O2. This shift allows O2 to be weakly attracted to the water molecule.
The next intermolecular force we're going to look at is called the dipole-induced dipole force. Now, dipole, as I said earlier, basically means you have something polar. Induced dipole means that you have something nonpolar. Now, a nonpolar species doesn't have the positive negatives like water has. However, when the temperature gets low enough, or if you put something really polar next to it, you can induce a dipole on something that doesn't have a dipole. So every time you see induced dipole, think nonpolar. So in the dipole-induced dipole force, you have something polar, something with a dipole, and something nonpolar, something with has to have a dipole induced on it. And so this is the next kind of force, and it's pretty strong. So for example, fish breathe oxygen even though they're underwater, and oxygen really is nonpolar, but somehow the oxygen gets in the water. That's due to the dipole-induced dipole force. The water has a strong dipole, and it induces a dipole on the O2, so it is able to make them dissolve, all right? And that's what gets the oxygen into the water, and the fish can breathe. So yeah, go dipole-induced dipole force. I like the fish, what can I say? So a dipole-induced dipole force is just something polar with something nonpolar. And there's lots of examples of how useful this is. In medicine, they use an iodine solution, which is usually iodine dissolved in ethanol or something like that. Ethanol is very polar. It has an oxygen-hydrogen bonding part to it, and iodine is nonpolar, but they are able to get the iodine in. It's used for sterilizing things before operations, stuff like that. So if you have a dipole-induced dipole force, you have something polar interacting with something nonpolar.
An iodine molecule has, on average, an electron cloud that is symmetrically spread over each iodine atom. I2 is not polar. The attractions or repulsions between the atoms of I2 molecules can distort their electron clouds. Dipoles can thereby be induced momentarily in neighboring molecules. In the flask is solid iodine. In the test tube is ice. When we heat the iodine, its weak induced dipole forces are overcome, and the iodine sublimes into the gas phase. The gas recondenses as a crystalline solid on the cold test tube.
Nonpolar compounds are nonpolar. They're literally symmetric. There's no positives and negatives, and they're pretty happy that way. However, nonpolar compounds will liquefy and solidify if the temperature gets low enough. So how they rationalize this is possible is that at really low temperatures, as these molecules get closer to each other, they start to induce dipoles on each other. So where there was no polar moment before, all of a sudden something polar comes out. And again, this is really low temperature. So this is seen as the weakest intermolecular force. It's useful if you want to crystallize iodine. So the lower right-hand video, the second one we watched, it showed how you can heat iodine gently so it goes into a gas, and then the gas iodine recollects on that test tube. It's called a cold finger. Anyway, its crystals form and stuff. Iodine is pretty easy to get to re-solidify because there's no intermolecular force. Iodine's pretty nonpolar. So if you hear about induced dipole, the ID force, this is the force between two nonpolar species, and it's definitely the weakest force of all. Induced dipole forces are important because otherwise, without them, all of the nonpolar things would never become liquids or solids. They'd stay as gases. And even helium, which is probably the most nonpolar species of all, can be turned into a liquid. All right, you can see in that table down there, helium will turn into a liquid at 4.6 Kelvin. So if you freeze helium down to just below, remember 0 Kelvin is where all matter stops, but at 4 or so Kelvin, solvent, that's where helium turns into a liquid. But anyway, the higher molar mass nonpolar species will have larger induced dipole species. So generally speaking, like if you look at the fluorine, chlorine, bromine, and iodine down there in the table, the boiling point goes up as you get to more complex molecules. It's easier to distort larger molecules than it is smaller molecules, or easier to polarize is the fancier name. So if you have to make a guess, higher molar mass means higher boiling points, even for nonpolar species, but it is easier to induce them, so that's why their boiling points are usually higher. So the question is here, which of the following would you expect to have the highest boiling point? And you have 4 noble gases. Now, all the noble gases are nonpolar, all right? They're just little atoms. So in this case, what we would do, since they're all nonpolar, they're all induced dipole, but what we would do is we'd pick the largest noble gas on there, because the largest noble gas is probably the easiest to have a dipole on it, and usually that's what happens. And again, if you can Google these things, you can confirm this. However, what I would do is I would pick answer D, because xenon is the highest molar mass of those 4 gases, so it should be the highest one and able to induce a dipole on it. So again, if you have to guess, if they're all the same intermolecular force, the highest boiling point will probably be from the biggest molar mass. This is a summary of the 5 intermolecular forces that we've seen so far. Ion dipole is strongest. You have to have something ionic and something with a dipole. So like sodium ions in water, chloride ions in water, etc., etc. Hydrogen bonds are stronger than dipole, so we'll put them next. Hydrogen bonds, you must have a nitrogen, oxygen, or fluorine connected to a hydrogen. Hydrogen connected to anything else, you won't have a hydrogen bond, but you could have dipole forces. So for example, there are some compounds with carbon that have, say, hydrogens on them. Those are not necessarily hydrogen bonds, but if the molecule is polar, then you'd have dipole. Anything polar will be dipole, but the only things that will have hydrogen bonds will be if N, O, or F are connected to hydrogen. Then you have the dipole-induced dipole force. That's where you have something polar and something nonpolar coming together. It is responsible for getting oxygen to the fish in the water, so that's why I think it's kind of cool. And then finally, you have the induced dipole force. This has other names: dispersion, London forces, van der Waals forces, whatever. It's the weakest of all of them. So anyway, induced dipole is the weakest. It's when 2 nonpolar species come together. No problem. This is a problem you might see. When potassium chloride dissolves in water, what kind of intermolecular forces are formed? Now, potassium chloride is ionic and water is very polar. So you're going to have the chance for ions, either K plus and or Cl minus, with something polar, which means something with a dipole, which is what water will do. So something ionic with something polar, i.e. something with a dipole, that's going to be the ion dipole force. K plus AQ when we write it, or Cl minus AQ, those are the ion dipole interactions that result. You're breaking the ion-ion forces in KCl, you're overcoming the hydrogen bonding in water even, and you're able to make then ion dipole forces, which is kind of a cool thing.